potential weather happenings. If the school is delayed till 10:30 on Wednesday because of weather issues, then we will start the test at 10:30 on Wednesday, and people are expected to be here. So so that would be how that happens. If for some reason the school is delayed until like noon that day, then we will have that test the next Monday, and you would be ready to also take your major vessels lab. You know exactly what's required of that major vessels lab, the arteries, major arteries, and the major veins. We talked about which PowerPoint slides that you would want to look at for those, and we talked about two things we added: the carotid arteries and the jugular veins, right? So if you did not hear that or see that, then you should make sure you get with somebody and or me and ask those questions. So everybody good about what's happening going forward. We're going to expect that we're going to be here at 9 o'clock on Wednesday. So please be ready for the cardiovascular system test. I am going to do a little bit of a review today. At the end of our lecture, we're going to take a break, and since there's not really a lab for the lymphatic system per se, there are a couple of structures in the lymphatic system that I end up adding to the respiratory system lab, but there's really no lab for this, so I'm going to use that time, a little bit of that time today, to do a really kind of quick little review for your test. So if I were y'all, I'd be here for that during that time. Okay, so we'll go over, we'll hit the highlights, things that I know that you'll be responsible for the test. Fair enough? Okay. Any questions from me before we get started with the lymphatic system? Do you have any questions? Okay. All right. So when we were talking about this lymphatic system, we defined quite a few things, and we talked about the idea that you have this entire vascular system called the lymphatic system that includes lymphatic capillaries that are picking up lymph from our tissues and returning that lymph eventually back to the bloodstream. But we said lymph comes from where? The bloodstream. It comes from blood plasma, the bloodstream, at the blood capillary level. So I walked through that with somebody in lab at the end of lab the other day. I took a drawing. But does anybody have any questions about what lymph is, where it comes from, and how it gets back to where it came from? Does anybody have any questions about that? Because if you do, this would be kind of the time to get this. Now, okay, so we're going to move forward then. And we talked about, as far as that lymphatic system goes, we understand that we don't just need to understand lymph and where it comes from and where it gets back to in those vessels. We also know that we have these organs, and I'm going to put quotation marks around that because they're little mini organs called lymph nodes, and what their functions are. And then also part of that is going to be our tonsils, and our spleen play a role in this too. So that's what we had talked about, and then we said that are most people born with the system, the lymphatic system? Yes. So we talked about two major types of protection: something you're born with, something that is non-specific, but we said there's another word for that is what? Innate, being that you're born with it. And this is one of those things, along with like skin and mucous membranes and tears and saliva, hair, all these things. These are protective, aren't they? And most people are born with them. They don't protect you against just one particular thing. They're non-specific. They protect you against a lot of different things. So this is what this is referred to. And all of these things are important, because if you are missing some of these things, could it compromise you and make you more susceptible to disease? Yes. So you could even say that like pain receptors, are they part of your non-specific immunity? Yes. Aren't they? So there's a lot of things you could think of that are part of this non-specific immunity that we would definitely want to have functioning, right? And would understand, because of their functions, if they were lost or compromised in some way, what you would lose, what your patient is now going to be susceptible to because of what they've lost. So Any questions about that? There are a couple of other things that might not be so obvious to you or might not be things that you thought about. And let me name some of those. We just finished our study of hematology, so we know exactly what neutrophils are. Oh, don't we? We know what neutrophils are. We know what eosinophils are. These are special types of white blood cells. You know, everybody came in here knowing that you had white blood cells, but you might not have known that you had so many different kinds, and that each of these different kinds have very specific functions. So we understand that neutrophils have these granules that are antimicrobial, and they fight against bacteria. Do they fight against just one particular kind of bacteria, or do they have antimicrobial granules that fight against a lot of different ones, right? So this is non-specific. You also have eosinophils that we said contain histamines. And histamines get a bad name because everybody wants to go get antihistamines whenever they hear about this. But do we say histamines have very important functions? Yes, so these important functions are to initiate those pain receptors. They're also to bring fluids to the site. They're going to cause vessels to become dilated and a little bit leaky so more fluid can come to the site. And when more fluid's coming to the site, more blood is coming to the site, more oxygen's coming to the site, heat's coming to the site. And would all of that be reducing the risk of infection? Would all of that be protective? Would it be? Mm-hmm. Yes, it would. Up to a point, we said. But yes, it would. So these are things that are kind of non-specific that we have. And we've already learned about them. Basophils. Basophils have histamine and they have heparin, which we talked about is going to be a natural anticoagulant. And you all know from your hematology study what coagulation is. What is coagulation? It's blood clotting. It's that third step of blood clotting. The first one was a spasm, the second was a platelet plug, and then there was coagulation, right? So you guys remember that for your test Wednesday. But coagulation, so we don't want unwanted coagulation, so heparin is going to be an anticoagulant, isn't it? So we know that this is going to do a lot of different things. We have these lymphocytes, and we talked about lymphocytes in adults. You know, usually are going to be about 30% of the circulating white cells, about 30% or so are going to be lymphocytes. But there are a lot of different kinds of lymphocytes. We've already known that there's something called T lymphocytes, and we said they're called that because they're dependent on hormones from the thymus gland. And we're going to find out that there are different kinds of T lymphocytes. But there's also these lymphocytes that are called natural killer cells. And I'm going to talk about another type of lymphocytes today called regulatory lymphocytes. But anyway, these natural killer cells are no joke. They're like your, they're like your policeman going around just seeing if there's anything foreign. And if there's something foreign, or if there's even your own host cell that is infected, then these natural killer cells are going to be right on the spot and take it and do their business, which is take these things out. We've got monocytes, which we said are the precursors to macrophages. This is all review, isn't it? This is kind of review for your test Wednesday, because you already know about all these cells, don't you? And these are non-specific. People are born with these. You're going to be able to have these that are going to protect you against a variety of things and a variety of different circumstances. And as long as they're working how they're supposed to be working, you have this innate immunity. So inflammation is innate. You know, we don't have to have an infection to get inflammation. We can cause trauma to tissue and inflammation happens, right? But we can also get inflammation when there is an infectious process also happening. It doesn't just happen specifically for one or two or three things. It's a non-specific type of thing. And I want you to know the 4 cardinal signs of inflammation. They are redness, heat, pain, and swelling or fluid or swelling, right? Edema. And are those things good things? Yes. Those things are very good things. Inflammation means that your body is responding, is trying to bring, guess what all those things come from? Those things come from your vessels dilating, bringing fluid to the site, bringing blood. What's the blood bringing? Those white cells I just talked about that are going to keep infection down. What else is going to happen? With the increased heat, it's going to increase metabolism, which is going to increase tissue repair. Inflammation is a good thing up to a point. And then if it gets over that point, can it become harmful? Can it become harmful? Yes. You know, so I think inflammation is sort of like pain. People think of it as all being bad, and we don't want to be inconvenienced. But they're good up to a point. Now, with that being said, let me just give you this little caveat here. So I will say this. A lot of times, especially in young people with really strong immune systems, a lot of times what we're dealing with after, you know, people who have strong immune systems, after they've had injury or after they've had insult or infection, sometimes the most damage is actually done by that inflammatory response. So do you have to monitor it and watch it and control it? Yes. Yes. If anybody's ever had a sore throat, it's your inflammatory response that's causing that pain and that whatever. But that's good because it's also bringing healing factors and protective cells to the side, right? So up to a point. Right. So does everybody know the 4 cardinal signs of inflammation? So actually, how does this happen? How does all of this happen? And I would want you to understand that when the cells are damaged, they're going to be releasing almost like alarm signals. And these alarm signals, guess what they are? Bradykinin, histamine, leukotrienes. Leuko meaning white. These trienes are going to be these chemicals that are released by white cells. They're like alarm sirens that are bringing this blood, this fluid to the site, right, and initiating pain receptors. So these are going to be the classes of chemicals that are doing that. But does all of this, if you look at this, does all of this sound like this is going to be helpful in repair? Doesn't it? Again, up to a point, but good. This is a little visual of some of that. So you got like a splinter coming in, and the splinter obviously isn't sterile, you know, stuck on sterile splinters. And, you know, whatever, even if it's a brand new nail, can you get an infection from it? Even if it's brand spanking new, can you get an infection? Yes, you can. So you step on something or whatever, it enters, and these damaged tissues and other white cells are going to cause deployment to the area of all of these healing types of situations that's going to happen. So anyway, just a basis for that. So tissue repair. This is going to help with the tissue repair, and great. I want to tell you about a substance called a molecule called interferon. There are a couple of different kinds of interferon, but that doesn't matter. Okay, so interferons, so these are going to be polypeptides. What do y'all know that means? What class of molecules are they? What class? Are they carbs? Are they lipids? Are they proteins? What are they? They're polypeptides. What are they? What'd you say? Why do you say that? Because what's the bond between amino acids? The bond between amino acids are peptide bonds, aren't they? So polypeptides, these are like protein in structure. So let me tell you where these interferons are released from. They're released from cells that have been invaded by viruses. So when you have a viral infection, those viruses are parasites. They can only act if they get inside your cells and take over your cellular machinery. And they're going to do that. And the cells that, most of the time, the cells that they invade are gone. They're going to die as soon as the virus has replicated itself. But before they die, guess what these cells do? They release this product called interferon. This is a naturally occurring product that you release. And interferon is going to be a siren to the neighboring cells to close their windows, close their doors, lock their basements, lock their front doors, because there's a virus, there's a pathogen in the neighborhood. So what interferon essentially does is limit the effect, limit the viral effect. So this happens with every cold you've ever had, every virus you've ever had. The cells will release interferon that limits the viral attack. So what a wonderful molecule, right? I want you all to know that we can actually synthesize interferon in a lab. And we can give it to people who have viral disease, and does it help to limit their attack and the devastation of that attack? Yes, it's been used very much effectively. It's also been used effectively as an anti-cancer type of treatment. So when this molecule was first discovered, first identified as doing what it does, it was thought that interferon was going to be the magic bullet against cancers. And that is because we could synthesize it in the lab, we now had this magic bullet, you know, sort of like a silver bullet for vampires, right? But this is going to be the magic bullet for cancer, that we could treat cancer, and this was going to be the cure for cancer. Now, has it turned out that way? No, it hasn't turned out that way, because we do understand that all cancer, like cancer isn't one disease, is it? It's a lot of different diseases depending on the origin of the tissues that are involved, and even the same types of cancer and the same cancer in two different people can act very differently. Yes, so it hasn't quite worked out that way, but it's still been really a wonder drug, you could say. So interferon is used. So everybody knows what it does, what the function of it. It's a protein, and our own cells make it. Our own cells make it anytime we have a virus, and it limits the viral attack. And then also, we can treat people with it as well. Now, guys, I want to talk to you now about, and these are all non-specific things, right? We all have the ability to have inflammation. We all have the ability to have, you know, all these things make interferon. But we also have, innately, we're born with recipes, and this is just the human species. Most of us are born with recipes to make proteins that are called complement proteins. And I'm going to want you to know what these are. Now, y'all writing that down. So, okay. Let me tell you what these complement proteins are. And before you write anything, I want you to listen to me. Do you remember, and this is part of your test, Lindsay, do you remember in hemostasis, the controlling of bleeding, right? In hemostasis, we had these clotting factors, which are just proteins that we inherit from our parents that act in our system, because they're always circulating in our system, in our blood plasma and whatnot. They're circulating, they're present. And if they become activated, there will be like this domino effect that we can get from fibrinogen, which is the first clotting factor, to a fibrin clot. And we call that coagulation, didn't we? And we said that it doesn't take long. You can actually, there's a certain timing sequence that's involved with both of those pathways. We want it to be just right. If you're missing any of the clotting factors, just like dominoes, was it going to affect fibrinogen getting to fibrin? Was it going to affect that? Yes. So do you remember that? Do you remember that you inherit proteins? What was it called when you didn't inherit maybe one of the proteins, especially the common one like factor VIII? When you didn't inherit that, it was called what? Hemophilia. So y'all remember that test, Wednesday, and also you just remember to be informed that that's called hemophilia, when you're lacking one of those blood clotting factors. Well, there's this whole other system called the complement protein system. These proteins don't have anything to do with blood clotting, but what they do have to do with is your immunity. And you inherit these, and they were named by when they were discovered, like complement protein 1 was discovered when? First. Did everybody get that? So anyway, they were just named that way. And complement protein 2 and 4 and 3 and so whatever. So I want you to understand that from your parents, most Homo sapiens have inherited all these complement proteins that they need. And if there is a invasion by a pathogen, these complement proteins become activated, just like the domino cascade effect that happened with hemostasis and coagulation. The complement protein activation is very similar. So one thing will get activated, it will affect the next, it will affect the next, and it will start this kind of cascade event. Okay? Yes?
When do they become activated?
When your cells become invaded by pathogens, or when your cells send signals that the complement system activation is going to happen. So typically it's when your cells become damaged. Your cells give off a signal to activate complement proteins. And we'll talk a little bit more about one of those activations in just a minute. Just hold it. Because you know, would you need this to be activated all the time? Or do you only need it to be activated when you need it, right? They're circulating around, they're kind of minding their own business, but when you need it, they're there for you. And let me tell you the 3 outcomes, because this is what's important. And this is what I will ask you about the complement protein activation. I'll ask you, what are the 3 potential outcomes, and what do these outcomes, what do they provide for you, right? Well, the first one is inflammation. Did we just say how good that is? Did we just say how good inflammation is? So y'all know the functions of inflammation. It's going to be bringing more blood to the site. The blood's going to cause heat to come to the site, which is going to increase metabolism, which is going to increase your tissue repair rate. That's all good. It's going to bring the heat that's going to help you, that if you've gotten microbes that are there that don't like that increased heat, is that going to suppress them? So we talked about how important inflammation is, right? So inflammation is one of the outcomes. The second outcome I want to tell you about is called opsonization. Opsonization, here it is on the slide, opsonization. Opsonization is this process of where the complement, see this bad guy that just invaded our system, guys? He just invaded, he's like a pathogen, he just invaded our system. That's okay, because we get a signal that he's the pathogen, and our, what'd you say? You'll remember, sorry. You sat on the front row, so people shouldn't sit on the front row if they don't want me to touch them. So anyway, but the, I don't mean to keep on it. So anyway, the protein, these complement proteins will literally stick to them and coat them. And what they will do is when they do this, it makes the white cells that eat the phagocytes, the monocytes that are our dump trucks, it makes them easier for them to phagocytize and eat and get rid of. Right? So that's a great thing, isn't it? So opsonization is this coating of the pathogens with these complement proteins so that they are easier to phagocytize. You know how you can think of opsonization? Sort of like trying to swallow a dry aspirin versus one that's got in a capsule. Has anybody ever tried to swallow a dry aspirin or something that was dry? Mm-hmm. You know, it's hard, isn't it? But if it's encapsulated, is it easier to swallow? Well, that's the same thing for your white cells. Easier for them to phagocytize, right? So that's opsonization. Isn't that a great thing? So we've got inflammation coming to get these bad guys and take them down. We've got them being phagocytized. That's actually a really good thing. But let me tell you the third thing. And this is a no-joke thing, too. This third thing that's a consequence of your complement proteins being activated is something called cytolysis. What did lysis mean? Split, and cyte means what? Cells. So let me tell you what these complement proteins will do. They will perforate the cell membrane of the pathogens, and actually they can even do this to your own cells, but if it's a cell that's been invaded. You know, if a cell's been invaded by a virus and it's been taken over by a virus, and viral replication is happening in your host cell, that host cell needs to go, right? So these proteins can perforate them, the membrane, and as soon as they perforate it all around, what have they done to that cell? Lysed it. That's called cytolysis. So that's the proteins actively killing the cell. But those proteins also can actively coat a cell so that it can be phagocytized, right? Are you good with this? All right, so these complement proteins. So could someone have an immune disorder? Could someone have an immune disorder where they were lacking a complement protein? Yeah, they absolutely can. They can absolutely be immunocompromised if they have not inherited one or more of these complement proteins. Now, your book does not address this, but I feel like I need to because I feel like it's something we should address here at this point. Have you guys ever known somebody who can fall and bump their knee and their knee will like triple size? Have you ever seen people who get bitten by mosquito bites or something? Now this isn't, don't go home if you know somebody that's like this and tell them they have a complement issue. But if they routinely over-inflame, right? If they routinely have this to abundance, like over the top types of reactions, I want to let you know, for these complement proteins, we said this is probably a positive feedback. Do you see this? This is a positive feedback. What did we say about positive feedbacks? That there must be a way to do what? Can you stay in positive feedback? No. So positive feedbacks are good things up to a point, aren't they? But they can't last too long because then they would become destructive, wouldn't they? So if you've got somebody who has this crazy inflammatory process, it's likely that they're lacking. Let me tell you what they're lacking. For a couple of these complement proteins, you also inherit what are called anti-C1, anti-C3. And they're the ones that are keeping it in check. But if you were lacking those, could you stay in the positive feedback too long and have an over-inflammatory response that then is like actually causing trouble? Can you? So anyway, that was FYI for you. That was just FYI. But these are positive feedback type of situation, and it needs to be kept in check. Are we good with this? All right. So fever. Do you only have a fever when you have an Escherichia coli infection? E. coli infection. It's the only time you have a fever. You only have a fever when you have influenza virus. No. Fevers are non-specific. Fever is your body's ability to change its thermostat. What an amazing thing. Your body's ability to change the thermostat. So what we understand is that most of us, and by the way, this is controlled by the hypothalamus. Did we say that's controlling everything else too? How does the hypothalamus control everything else? Because it's controlling what? It's controlling the pituitary secretions and the stopping of those secretions. So the starting of the pituitary secretions, but also the stopping of them. And it's controlling other hormone things. And now we're saying that it's the hypothalamus that's also controlling your thermostat. And that's really true. So when somebody, this is in Celsius, so 37 degrees Celsius, you normally, your thermostat, you're just moving around the set points, right? You don't keep the same temperature. Your temperature changes, frequently depending on what the environment is and depending on your metabolic state. So when you're sleeping, is your temperature the same as 10 minutes after you wake up and get up? No. So temperature's changing. You're around set point, usually around 37. Everybody's got their own set point. And it's good. And it's your hypothalamus that said it was that. But then your body is fighting. Your body is fighting something, either because of trauma. Can people have normal temperature increases, fever, if you will, after surgery? Isn't that, because that's trauma, isn't it? Or after a serious injury, and or after invasion of viruses, and or after invasion of bacteria. So it's non-specific. Your body can reset its thermostat. But what will happen is the hypothalamus will reset this thermostat, and as the body temperature is increasing, this point is getting higher. When it gets to this new set point, what you should see is that they're vacillating around that new set point. So this is referred to as the new stadium. As long as they're doing that, you should leave the fever alone, because is it protected? Fever is not a bad thing. It's protected. It might make you feel like hell, but it's protected as long as it's vacillating around this new set point. The problem comes in when fever is not setting at a new stadium. It's continuing to do what? Then it becomes a big problem, because then you have to stop it, don't you? I want you to understand that when your cells are damaged, either by trauma or by invasion of viruses and or bacteria, when your cells are damaged, they put off something called pyretics. What does pyromania mean? What is pyromania? Anybody know what that means? Or you're addicted to fire. That's exactly right. You have a fire addiction thing. So pyretics are going to be chemicals that signal an increase in temperature. That's what they're called, pyretics. And your damaged tissues put off these pyretics. But most of the time when somebody knows their temperature's going up, they take an which is antipyretic. Or you can take anti-inflammatories, but then also, and sometimes they act as antipyretics too. or you can take it specifically, antipyretics. So anyway, that can sort of stop this process. But as we said, you know, we do understand that fever is actually protective. It really is. So a pyretic is the chemical that's raising your temperature. Does that make sense to you just from the origin of the word? And so then when people have that, they take what? Antipyretics, don't they? Now look, what should happen in a normal course is that after the fever has done its job and after the tissues are starting to repair, you will go back to your set point. As the body temperature is dropping, you guys, this is known as defervescence. Defervescence is that body dropping back to the natural to the normal temperature. And there's certain signs and symptoms some people are really sensitive feel that when that's happening. But anyway, so these are just the different talking about fever. And is it non-specific? Yeah. So it isn't against just one specific thing. So maybe since I have been saying that over and over and over again, you guys can hardly wait to hear about what is specific immunity, right? Right? Everybody excited to hear that? Okay. Thank you, Sarah. Okay, so here we go. I could use the notes, but I'd rather draw my own. All right, so you ready? All those things, and you could probably think about other things in your body that you know are non-specific innate things. We talked the other day about just the act of, how about the act of vomiting? Is that actually protected? Is vomiting protected? Sure it is. Because usually when you're vomiting, you're getting rid of something, some sort of toxin, aren't you? Aren't you you're trying to get rid of? I mean, natural vomiting, not like induced vomiting, but natural vomiting. That's very, very protected. How about coughing? Is that protected? How about sneezing? Protected? So think about all the things you could think of that are just things you're born able to do that are protected. They're non-specific and they're kind of protected. All right. But now, I want to let you know, and this is like the main part of this, and this is your specific immunity. And I need you all to know it so well you could teach it about it. And you know every little part of the story. How do we learn? Through memorization or through stories? Through storylines, things that make sense, things that have a beginning, a middle, and an end. And things that, you know, consequences, and sequential things. That's how we learn, right? So this is how I want you to sort of get this, and this is how I really need you to know every part of the story. So here we go, specific immunity. It is why you get to get out of infancy. It is why you don't get put in a bubble, a sterile bubble, and not allowed to touch another human's cells, tissues. It is why you don't have to have sterile food and sterile water. It is why we don't need sterile air even, right? It's because of our specific immunity. Are you excited to hear what's involved? Okay, all right, I hope so, because it's important to know. All right, so when you're talking about specific immunity, is it sometimes referred to as adaptive? What does the word adaptive mean? What'd you say? Yeah, like you can adjust to something that you encounter. Right? You can adapt to it, and that's exactly right. For specific immunity, there are two major parts of specific immunity. Now they're happening at the same time, but I can't talk about them at the same time because I haven't just figured out that trick yet. So we'll talk about them one at a time, but you would understand that in your body, they're happening at the same time, right? So I want to talk to you about first, the two types. The first one I'm going to talk about is called humoral immunity. Humoral immunity. And after I finish that, I'm going to talk about cell-mediated. Okay, but we understand that these two things are occurring at exactly the same time. So let's imagine, I don't know why I always use little triangles, but let's imagine a foreign body has just entered our cells, and its little antigenic structure, which we're going to call its outfit. And antigens are proteins. You would want to know antigens are proteins. its little outfit looks like this. It's a very specific shape. And have you ever seen this? Has your body ever seen this pathogen before? Has your body ever even seen it before? Never seen it before. So, never encountered this particular thing before. This is unique, it's new, and it's now invaded the body, either through the nose, or through eyes, or through the mouth, through skin. Can we get things through our skin? We get a ton of stuff through our skin. But this has invaded the body somehow. And your body's never seen it before. Your immune system's never seen it. So let me tell you what happens humorally. And when you think about humors, I want you to know that that term means the fluids of the body. The fluids of the body. Humors mean fluids. Name some fluids of the body for me. Saliva. Name something else. Blood plasma. Blood plasma, right? Name something else. Urine. Name something else. Okay, name something else. Dakota, no one here. Right? Saliva. Did we say saliva, tears, breast milk? How about lymph? Nobody said lymph. You're still not thinking of lymph, are you? It hurts my feelings if you're not thinking of lymph. But they're the fluids of the body, right? So you're thinking about these fluids. So what could be in these fluids that could be protected? What could be being put out in the fluids that could be protected, that are going to be circulating around in the fluids of your body? By the way, you're all wet. You know, most of us, most of what we are is water, isn't it? Right? 65% of that water is actually inside of ourselves, but it's water. And it's moving in and out, bathing ourselves, blood plasma, whatever, but we're all wet. So this is talking about what are in these fluids of the body. And it's referred to as humoral immunity. So what I want you to know, for humoral immunity to be effective, you have to have effective B lymphocytes. Oh my goodness, we know that lymphocytes protect against viruses and cancer and whatnot. And we've heard of T lymphocytes, but here's another type of lymphocytes. They're called B lymphocytes. So what's going to happen with these circulating B lymphocytes? And this is all this is all they do. Let me just tell you, this is all they do. B lymphocytes are looking for something, an antigenic determinant they've never seen before. They're looking for something foreign. And if these are, by the way, inactive at this point, these are the inactive ones. This is writing where I don't have my pencil. So this is why it's so weird. But anyway, these are inactive, and they have one function circulating around in your bloodstream, and that's to look for a foreign antigen. And when they find it, guess what they do? They don't destroy it. But what they do is they actually take it in, they study its structure, its molecular formula. They undergo mitosis. What is mitosis? What does mitosis mean? Division, cell division. They start dividing, and when they're dividing, they become what are called plasma cells. Plasma cells. And by the way, these are very specific plasma cells, and, well, I'll tell you this later, but these plasma cells, let me tell you what they're going to do. These plasma cells are very specific. They've got one function, and that's to produce, a protein, oh God, I'm messing that because that's just a mess. They produce a protein called antibodies. These antibodies are going to have the absolute complementary structure to that antigen. These proteins called antibodies are going to have this absolutely complementary structure to that antigen. So I'm going to tell you what they do. Remember that pathogen over there that we called what? What did we call that pathogen? We call that pathogen what? We called him Dylan. He's our pathogen, right? So a B lymphocyte is going to at first be notified that you are a pathogen. A B lymphocyte is going to take you in, study your shape, start dividing, making plasma cells, many plasma cells. And those plasma cells, they're so prissy. I'm going to tell you, they're the prissiest things because they don't want to destroy him, you know, man to man. They're going to make an antibody that has the shape of him, and they're going to attack him. They're going to attack that. Those antibodies are going to attack that antigen. And as they attack that antigen, are they going to be removing them from the system? As this antibody goes in and hooks up with this very specifically shaped antigen, foreign antigen, they're going to be able to remove them from the system. Right? Did the actual plasma cells get up closer? No. The plasma cells were just pumping out into the fluids of the body. What? Antibodies, which are proteins that are specifically made to that exact shape of that what? Foreign antigen. Are we good with this? Do you have any questions about this?
How did you put inactive?
Well, these are inactive until they get notified of this foreign antigen, and then they become active, right? Now, let me ask you something. Can these plasma cells ever fight against a different foreign antigen? No. Are these plasma cells going to be around for a whole long time, or are they just going to be around in time until you get rid of enough of this foreign antigen? Is that right? That's actually right. So hold on. Now, wait a minute. I told you at the same time that these pathogens were coming into our system, these little pathogens that we never seen before, that have this very specific shape that we never seen before, that there was another type of a specific immunity. And that's called cell-mediated immunity. In cell-mediated immunity, let me tell you what you have to have. You have to have what are called cytotoxic T lymphocytes. These are very specific lymphocytes, these T lymphocytes. They're sometimes called T8 cells. They're sometimes called CD8 cells. I can't help it. I didn't name them all those names. I didn't give them all those names. I wish there was just one name for them, but they aren't. Why do you need to know all three names, do you think? On lab reports, depending on the lab might call them what? Cytotoxic T's. Or you might have a lab that you're getting results from that call them what? Or you might have a lab that's calling them what? And I would wish they'd start all calling them these, but that name, but they don't. But so you've got different names. But this is the same type of cell, isn't it? Now it's inactive. You have these circulating around. These cytotoxic T cells that are inactive, they're circulating around. But when they get a signal that there's a foreign antigen, do they become active? Then do they become active? Yes, and what do they start to do? They undergo what? Mitosis. But do you all remember how the prissy plasma cells produced their proteins that went into the fluid to do this destroying? I call these plasma cells the Air Force because they're dropping the bombs, right? But here are the Marines. The Marines they don't need the antibody because they're coming right up to you. That's why it's called cell-mediated, and they're destroying. So you've got these activated under mitosis cytotoxic T's that are just taking these pathogens out, hand-to-hand contact, cell to cell, right? But at the same time, you have antibodies bombing them, right? So this is actually what's happening. Are you good with this? So these under mitosis, these cytotoxic T's that are very specific to this, they can only fight these. They start multiplying and they start attacking. So as these are attacking and as this is attacking, what's happening to the numbers of these? They're starting to go down, and they have been destroyed. They have been causing your tissues damage, but they're being taken out, aren't they? Are y'all good with that?
So
guess what?
When the cell-mediated does mitosis, what does it become?
It becomes an active
Okay.
cytotoxic T cell. So now it's an active cytotoxic T cell, It's active against that particular pathogen. It's going to start doing cell-to-cell combat. It is not going to send an antibody to take it out. It's cell-to-cell. That's why I use those analogies, because I think most people can kind of get that, right? So you have these two things going on at the same time. Whenever you've gotten invaded by something foreign, guess what? If that were the end of the story, we would never get out of infancy. So that's a beautiful story so far, but it's not complete yet, and it's not what happens in normal immunity, normal specific immunity. Let me tell you the beauty of this. The beauty of this is this. You see these plasma cells? These were the active B lymphocytes become plasma cells and start pumping out antibodies. But you know what else gets made? A few memory Bs get made. Memory B cells. Just a few. These memory B cells get made. Yes. When this undergoes mitosis, plasma cells are made, but a few memory B cells are going to be made. Hey, guess what? When this cytotoxic T cell becomes active and undergoes mitosis and has all these cells that are doing hand-to-hand combat, guess what else gets made? A few what? Memory what? Memory T cells. It's T8 cells. A few memory T8 cells. So you know what? You learn this foreign antigen when it first invades you, and you learn it, and you combat it, and you fight it. But does it make sense to you? And listen, that this has to make sense. Does it make sense to you that this takes a little while the first time? The first time you ever get exposed to this, it takes a while for your body to study this foreign antigen, for those cells to become active, undergo mitosis, and for those cell numbers to start increasing, and then them starting to combat that antigen. And guess what's happening the first time that's happening? Guess what you've got? Signs and symptoms of disease. Because the signs and symptoms of the disease are happening. But then you start to feel better. Guess what directly correlates with you feeling better? Guess what directly correlates? The amount of your antibodies going up and the amount of the numbers of your CD8 cells going up. And as those numbers are going up, your antibodies and your CD8 cells are going up, your signs and symptoms are going away. Are we good with that? So the first time you get sick, or it might be minor, but you do get sick. And usually it takes a little while for this to happen the first time. But you know what the beauty is? The second time you get exposed, does it even take minutes? It doesn't take minutes before what become active. Before what become active? The next exposures. The next time you get exposed, on the next exposures, what do you have available right there just waiting to see that particular antigen? You have your memory cells. And because you have these memory cells, this is what is meant by that you can never get the same thing twice. And it is really true. People who have strong immune systems will never get the same thing twice. I know you all hear about people who say or think that they did, but if it's something that has what's called a stable antigenic outfit, you don't. You don't get it twice. You don't. And why not? Because you have what? Memory. You have memory in the form of what two cells? Memory B cells and memory what? T cells. Are you telling me for every foreign antigen that you've ever encountered, and that means when the amniotic sac broke and you were encountering even normal vaginal flora, right? Microbes. Are you telling me for everything you've ever encountered, you have very specific B and T lymphocytes? Yes. Those memory and B cell, T cells, those memory cells have to live for decades, and they do live for decades circulating around. Do the plasma cells live for decades and do the first initial active CD8 cells live for decades? They only live long enough until your signs and symptoms go away. But what will be circulating forever? The memory ones. That's beautiful. Okay, so everybody good so far? Everybody good so far? All right, now, I want to tell you something else that's just as important as every step along this way. Did anybody have any questions about what an antigen is? Does anybody have any question about what an antibody is? No? Okay. When we talk about self-antigens, like all of our cells have these self-antigens, what does that mean to you? What does that mean to you, that we have self-antigens? Our cells have a very particular set of self-antigens. What does that mean? Well, why don't our immune system cells fight our own self-antigens? Because these cells are actually schooled, and that's literally the truth. Before they get pushed out into the peripheral blood, they get schooled on what is a self-protein and what isn't. And if they don't do the right thing, they get destroyed before they get pushed out. So our cells, our white cells, our immune system cells don't usually fight against our own self-antigens, do they? Sometimes when there's a cross reaction, what do we call that disease? Autoimmune diseases. But usually we don't. We recognize what's foreign. We never have to get something again the second time because we have these memory cells, and we don't get some things over and over again as long as it's a disease that had a stable antigen structure. You don't get the disease again. The influenza virus is a virus that you can get over and over. Why? Because it changes its antigenic outfit. It changes its structure. An article just came out this week to tell us that this influenza vaccine this year is way more effective than last year's. You know, they have to predict what they think that antigenic structure is going to be in the next time it goes around because it changes so frequently. But the vaccine can really protect people, not just you. You know, if you're young and healthy, you'll probably get over the flu, but you don't want to have it, because if you don't get the vaccine and you have it, and your grandmama or your little baby niece dies from it because you exposed them to it, it would be a hard thing to get over, right? So you don't get just the vaccine to protect you, do you? You get it to protect other people. And this year's, luckily, we never know exactly how effective it's going to be, but this year's is pretty effective. They're pretty happy with how effective it's been because it's been a pretty rough season. A lot of people, you know, not everybody can get immunized, but anyway, some people, it's not advised for them to get immunizations of their immune system. All right, so we get this. Now I have another part of the story. Just like I told you how beautiful humoral immunity is, because you're making these proteins that are going to battle, and how beautiful cell mediated it is, because you're going to be making cells that will battle foreign agents. But that's beautiful, but we said the real beauty is in the what? Memory. Because the memory means that they're ready for the next time, and are they going to have to spend any time studying it, or do they already know what to do? They know exactly what to do, and within minutes of exposure, you have these cells activating. I give the example of I had chickenpox when I was little. I don't remember because I was too little. But I give the example of my 3 kids all had chickenpox at the same time. So the whole house was full of pox, right? I've never seen so many pox. So it was just so much. Do you think I wasn't being exposed to that virus? I was wiping that virus in my nose and in my eyes, and I was swallowing that virus. It was just all over me, that virus was. But did I get sick? No, because within minutes, these cells that live for decades are protecting me. I will never get it again, because within minutes, my antibody amounts, because of these memory B cells, my antibody levels went sky high within minutes. Because did this memory B cell have to like study it first? The first time I had chickenpox, it took a while before my inactive bees learned the antigenic structure and started to undergo mitosis. The plasma cells started pumping out antibodies, but while it was doing that, I had signs and symptoms of chickenpox. I was sick. But as soon as these numbers of antibodies went up, as soon as my CD8 cell numbers went up, I started getting over my signs and symptoms and I got well. Is that right? But on all subsequent exposures, and that's not the only time I've been exposed to chickenpox since I was a baby, I've been exposed many, many times, and that's okay, because these memory cells, they have one function, and that's to look for that particular virus, and they're going to immediately pump out antibodies. I want you to write down the word titer, T-I-T-E-R. T-I-T-E-R. A titer simply means a quantification. You're trying to find out how much. So when I tell you that these antibody amounts are going up, what I'm telling you is the titers are going up. Is that good? Everybody good with that? So for the memory B cells, does it take long to get detectable titers of that antibody? I'm telling you, minutes. It takes minutes before those titers are going up. It's why, even though I was swallowing and inhaling and just all over the place, viral, chickenpox virus, I never got a sign or symptom, did I? Because these protect me. So think about that for everything that you've ever encountered like that. You have these circulating cells that are so protected. Now, does everybody understand what I've told you so far about specific immunity? Because I have one really other very important question. Ready? So far, we've learned about B lymphocytes becoming plasma cells and memory Bs. So far, we've learned about CD8 cells, cytotoxic T cells, becoming active and more numerous and making then even memory T, CD8 cells, right? And so far, these two cells do this in response to a foreign antigen invading your system. And by the way, we live in a foreign world, really. We've got all kinds of things that are in our ecosystems that we have to adjust to, right? Okay, so I need to tell you about a different kind of cell. This cell is so important. Like, I'm going to use red, I guess. This cell is called a CD4 cell. It is a very special kind of T lymphocyte. Did I promise you all I was going to tell you all about some different types of T lymphocytes? CD4 T lymphocyte. Let me tell you about this cell. This is also on some lab reports, sorry, not my fault. On some laboratory reports, this will be called a T with a little H down here. That little H stands for helper T cell, a helper T lymphocyte, a helper T. Let me tell you what we know the helper T lymphocytes do and how they're involved in this specific immunity. And I need everybody paying attention to this. These helper T lymphocytes are the ones that notice when something foreign comes in. They're the ones that are sending those molecules that will wake these inactive cells up and say, you got to turn on right now. You got to take this foreign thing in and whatever. So what could you say about the helper T, the CD4 lymphocytes? They're the what? Well, they are communicators. They are communicators. But could you say, do you all see that your entire specific immunity is depending on them? Your entire specific immunity. We know that these chemicals that they're sending out, these cytokines, some of them are like that. But anyway, they also are causing the complement system to become engaged. And the complement system, we said, was really non-specific. But do you remember the complement system that was going to give us inflammation, cytolysis, and oxidation? You remember that? the complement system was pretty important, those proteins. So we've got these cells. We've got these cells that are really kind of the cornerstone, I don't know what to call it, linchpin, cornerstone, you know, that if they are pulled out, what collapses? Specific immunity. So if you have a normal person that's going to have about 600 of these cells per microliter of blood circulating around at any given time, there is a virus that attacks specifically those cells. The virus that attacks specifically those cells can take those cell numbers down to 200 circulating per microliter. And if they ever do that, you're in full-blown AIDS. So the HIV, which is the human immunodeficiency virus, the reason it is so devastating to the immune system is that it attacks, it has these special receptors for what cells? Which T? You can't say T cells anymore in this class. Why not? Because now y'all know that there are a lot of different types of T lymphocytes. So which cells? CD4 or T4 or helper T, right? It attacks those cells. And over time, if those cell numbers go down to lower than 200 cells per microliter, that's why on lab reports you'll get that number. You'll get a number for the T4. Sometimes it'll say CD4. Sometimes it'll say helper T, lymphocytes. But you'll get a number. And if you get that lab report, what do you know your patient has? They would only be looking at that for patients that are HIV positive. Because they're, you know, just because you're HIV positive, does it mean you have AIDS? No, it means you're HIV positive, and you can certainly be spreading it around. But they're going to watch, and they're going to watch that cell count number, and once it gets low, guess what we're starting to see? As it's starting to become low, we're starting to see those patients getting opportunistic diseases, things that should not be making them sick. They will have cancers that we only see in immunocompromised patients. They will have pneumonia from fungi that we don't see in any other patients. They will have encephalitis, inflammation of the brain, from viruses that do not invade a healthy person's central nervous system. So they get what are called opportunistic diseases. An AIDS person will never die from an HIV virus. The virus is taking those cells out, and then they end up dying from opportunistic diseases because of it. Does that make sense? Does everybody hear what I'm saying? So indirectly, of course, they're dying from their HIV status because that took out their most important cells for their specific immunity, and their specific immunity collapses. Yes. Over 600 plus. For the CD4 cells? Yes. All right, so this looks like a crazy found notes, like a crazy thing, but were you all following me? Were you following me? So I will ask you things, not Wednesday, because Wednesday you have a test, but for the next Monday, am I expecting you all to know quite a bit about the lymphatic system, and including anything we've talked about with the lymphatic system to this point? I really will expect that. And what I want you to know, what I'm going to want you to know is both non-specific lymphatic and non-specific and this specific immunity and what's involved in this specific immunity, right? And if I were to ask you, what does humoral immunity mean? It means the protection you have in the fluids of your body. And what do we know those proteins are called that are going to be protected? They're called antibodies. They're proteins. Don't call an antibody to me a cell, okay? Cells are different from proteins. They're proteins that are made by very specific cells called what? They're B lymphocytes that become active, and then they're called what? Plasma cells that produce antibodies. Is that right? Is that right? And then those antibodies get released into the fluids. This is why your saliva is protected. It's why your tears are protected. It's why breast milk is protected for the newborn. Because what's circulating in there? About, you've got a GI tract, a 30-foot tract that's just filled with fluid and mucus. But guess what's in that fluid and mucus? Antibodies that are protected, right? So you've got them in these fluids of your body. Now, and you also have when foreign things invade. You have cell-mediated, which we said is cell-to-cell combat, isn't it? And cell-to-cell means that as these become active, they're going to do just direct cell-to-cell attack of these, but they're also going to form these memories. Both of these form memories. And this is why you don't have to stay sick your entire life until you die. And you would die very young if you didn't have this. Right? Specific immunity. All right. I don't have any questions. I have one more thing I just want to cover for today, and then I'm going to just stop and do we're going to take a quick break, and then I'm going to do a review for the class for Wednesday. I'm going to do just a real, I think a little review, so hopefully y'all take notes on this. All right, so guys, so we said that when we think about foreign agents, whether they're viruses or bacteria or protozoa or fungi or whatever, or even if they're bacteria, even within the same genus but different species, that each one of them had their own outfits, their own antigenic determinant sites. They're referred to, you don't need to know that, but their own outfits. I call these proteins antigens. Okay, I call these proteins antigens. And we understand that if you see one that has a particular shape that you've never seen before, what did I tell you you will make in response to it? Antibodies. And do you know what cells produce antibodies? Sure, you do. And I just told you, but you can go back and review. But what I need you to know is that not all these antibodies classes are the same. There's like 5 different classes of antibodies. And this is kind of just really kind of, sorry, nerdy a little bit, but they're based on their organic molecular structure, these classes are. And here's what I want you to know. I want you to know it well, but it really is all I want you to know. And if you want to dig deeper, fine, if you have more time. But this is what I'm going to ask you about. Y'all remember my storyline, and I told you the first time you get exposed, you make plasma cells that produce antibodies. Is that right? That class is actually called IgM. That class is the primary immune response. They're the primary immune response. So that's the class IgM. Are you with me? Then I told you that you won't just make plasma cells, you'll make a few what? Memory B cells. And the next time you get exposed, this is the class. It's going to be IgG. They look slightly different. They actually have a slightly different antibody structure. They're still going to be fighting against that specific antigen, but the structure is slightly different. That structure slightly different allows for this class of antibodies to cross the placenta. So let me ask you something. If I was pregnant a few times, and so during my fetus's growing, if I got exposed to chickenpox virus, somebody who had chickenpox virus, did I have to worry about my fetus? My fetuses? No, because my antibodies crossed the placenta and would have protected them. When my fetuses were born, were neonates, they had my circulating antibodies, my IgG antibodies for anything I'd ever had that protected them for a short period of time. Now, do proteins last forever, or do they have a shelf life? So I tell people, yes, it's true that neonates are usually protected by mother's circulating antibodies that were IgG that could cross the placenta if the mother had them, and could cross the placenta for a very short period of time. It doesn't mean you should take them to Walmart and let everybody stick their fingers in their mouths. Don't do that. But they do have some protection from the mother for short periods of time. And then that protection, those proteins start to break down, and they're going to have to build their own after that, right? Do you get what I'm saying? Okay, so does it make sense to you that the IgG, since these are the ones that we do on second exposure, and the ones that can cross because of their shape, does it make sense to you that these are the predominating antibodies that you have circulating? Does it? Well, it should. So you would want to know that. Predominating. You only have IgM when what? When you're first exposed. I want you to really be listening to this because this is going to answer a micro question that you had that was a little bit ahead of the rest of the people. Okay? Right? So you're listening to these classes of antibodies, right? Okay. IgA is a molecular structure of an antibody that we find in saliva, tears, breast milk, intestinal secretions. So these are in those secretions, and it's a type of IgA antibody. This is incredibly protected. These are incredibly protected. This is why they tell people, even if you don't want to breastfeed, if you can even pump for a few days, and colostrum, that first milk is rich with IgA mothers, IgA antibodies. And if the neonate can just get that, it can coat their little systems. It can really get them on a good start. I mean, if you would want to do that, you know, but whatever. So you get what I'm saying. All right. Now, there's also something called IgE class. I don't care about D. I'm not even going to ask you about it because I don't think you'll ever hear it again. But IgE, you will. IgE are these antibodies that are going to be formed in response to allergens. Maybe you all can remember it because you already know eosinophils are special white cells that are in response to what? Y'all should know this by today. These are eosinophils are in response to allergens and parasites, right? And they have histamines. So IgE are this class that we're going to see when people are having allergic types of reactions. Are allergic types of reactions ever fun? I don't have any allergies, but I wouldn't think they would be fun because I've seen people who do. Okay, I've seen it and it's ugly and it can be ugly, right? And I don't mean just aesthetically. I mean just poor people because of the signs and symptoms, right? But here, if you've ever heard of allergy shots, you don't need to know this, but I'm just letting you know. The way they do those serially diluted antigenic shots, where the first one you don't get anything. But afterwards, they give you very tiny amounts of that antigen, the allergen, the antigen. And the next one, you get a little bit more, and a little bit more, and a little bit more. They're trying to get the person to convert and stop producing IgG, and start producing IgG. Because when you have IgG antibodies, do you ever feel a symptom? Did I ever feel a symptom when I got re-exposed to chickenpox? No. IgG, if a person has strong IgG responses, they don't get it again. Do you hear what I'm saying? All right. So, why do I care that you all know those 4 classes and where you see them and when you see them is this. You can use the titers of those. What's a titer? It's finding out how much somebody has circulated. You can use the titers to diagnose somebody of disease. If somebody comes in and you ask for a titer and they've had symptoms for a long enough period of time, by the way, does it take a little while to be able to build up IgM on initial exposure? Does that take a while? Guys, does it? I want to show you one more this slide and then I swear I'm good. It takes a while, doesn't it? But if they've had signs and symptoms of the disease for a while, and you order a titer of IgM, and you're seeing that titer go up, is that your answer? Is that what's causing their disease? Hey guys, that's your answer. That's what's causing their disease. The bad thing is that sometimes in a lot of these tests for antibodies, they're non-specific. So what they're really looking at is IgG. They're yay or nay that you have it. And just because you have IgG, let's say you really got signs and symptoms and you're sick and it looks like something that, like, let's say mononucleosis. But if you did a non-specific titer for mono and you see that it's positive IgG, they don't have that now. They had that a long time ago. Do you get what I mean? They would always look positive for it if you did that test. That's why you have to be specific in which class you're ordering. And you have to know what you're ordering. They're referred to as heterophilous antibody studies. And a lot of times that's not what's being done. It's more just of a yay or nay. And if it's a yay or nay, it can be confusing in the diagnosis. So you have to know what you're ordering and what's coming back to you. So anyway, first class that's on its first initial exposure, IgM. The predominant class that's mostly circulating around because you've been exposed to all these things in the past and then you cross the placenta, IgG. Allergies and parasites, IgE, and then in saliva, breast milk. Okay, so we good? Antibodies are good things? Antibodies are good things, unless they cross-react with their own self-antigens, then what? Then they're not good things. Let's take a 10-minute or 12-minute break, and then I'm going to come back and I'm briefly going to give you all a review, okay, for this test that's coming up. 12 minutes. I'm not going to record it. Does that seem mean?